All right, so when you think about how machine reads text, what comes to mind? Probably something like building with blocks, right? Sticking little pieces together to make something bigger. But what if I told you that's kind of backward? What if the key to understanding language isn't about building at all, but about carving? Well, that is the absolutely fascinating idea at the heart of the Unigram algorithm. So you've got these two totally different ways of thinking about it. On one hand, you have methods like, say, byte pair encoding. And yeah, those are the builders. They start with a pile of single characters and patiently, piece by piece, merge them together to build up a vocabulary. But Unigram? No way. Unigram is a sculptor. It starts with this huge, messy block of all the possibilities and then just chips away. It methodically carves off all the useless bits, the stuff it doesn't need, until what's left is this perfectly sculpted, ideal vocabulary that was hidden inside all along. And look, this whole sculptor's approach isn't just some neat little analogy. It's not a thought experiment. This is the real deal. It's the engine humming away inside SentencePiece, which is the tokenizer that powers some of the biggest models you've heard of. We're talking Google's T5, Albert, XLNet, you name it. So yeah, this method is out in the wild, doing the heavy lifting at a massive scale. Okay, so let's stick with the sculptor idea. If Unigram is the sculptor, how in the world does it know where to put the chisel? How does it decide which parts of the marble to chip away and which to keep? Well, that's the magic, and it all goes down during the training process. So here's how it works. It's basically this big, repeating loop. First, it starts absolutely huge. I mean, a massive, oversized vocabulary with tons of potential tokens. Then it calculates something called a loss score. You can just think of this as a report card. How well is our current vocabulary doing its job? After that, it does the really clever bit. It hunts for the weak links. It identifies the tokens that are, well, kind of useless, the ones that barely help the score at all. Then it makes the cut. It just removes a chunk of them, say 10%. And then it does the whole thing all over again. And again. And again. It just keeps looping, refining, and carving until that vocabulary is sculpted down to the perfect size. Okay, but wait a second. I just said it hunts for the weak links. But how? How does it actually know which tokens are the weakest ones? Which ones have the least impact? To really get that, we need to zoom in. Forget the whole vocabulary for a moment, and let's look at how Unigram decides to split up just one single word. All right, section 2, tokenizing, finding the best path. Let's see how Unigram actually splits a single word. The entire secret sauce behind Unigram is one thing: probability. It's actually pretty simple. The model just looks at all the training data and figures out how often each potential token shows up. From that, it gives every token a probability score. So when it needs to tokenize a new word, it looks at all the different ways you could split it up, and it just picks the one where the combination of token probabilities is the highest. That's it. It's just a game of finding the most likely path. Let's make this super concrete. Take the word pug. Okay, one way to split it is just into single letters, P, U, and G. Fine, but maybe in all the training text, the combination PU or UG shows up all the time. If that's the case, those tokens will have much higher probability scores. So the algorithm just does the math. It multiplies the scores for each possible path, and whichever path gets the highest final score, well, that's our winner. Now you might be thinking, okay, for a pug, that's easy, but what about a super long word? Wouldn't checking every single combination take forever? And you'd be absolutely right. It would be insanely slow. That's where this really clever tool called the Viterbi algorithm comes into play. You don't have to get bogged down in the math, just know what it does. It's a super efficient shortcut. It lets the model find that one single highest probability path without having to check every single possibility. It's a lifesaver. All right, next up, the engine of training. This is where we connect the sculptor's chisel to the stone. So we've just seen how Unigram splits a single word, right, based on probability. The big question now is, how does that connect back to our sculptor, to that big training loop where we're chipping tokens away? Okay, remember that loss score we talked about in the training loop? Well, this is where it comes back in a huge way. That loss score is tied directly to the probabilities we were just looking at. The easiest way to think about loss is as a badness score. If your vocabulary is finding tokenizations with really high probabilities across the whole data set, your badness score, the loss, is going to be really low. And low loss is good. It means your vocabulary is doing an awesome job. So here's the million-dollar question. What actually happens to that loss score, that badness meter, when our sculptor decides to take the chisel and chip away a token from the vocabulary? Let me show you exactly how it works. Let's say the token hug is currently in our vocabulary. So when the model sees the word hugs, it makes a nice, clean split. Hug and S. This combo has a high probability score. Everything's great. But now, let's get rid of the token hug. We chip it away. Now what? The model is forced to find a new path. Maybe it splits hugs into H, UG, and S. And guess what? That new path has a lower total probability. And when the probability goes down, our badness score, the loss, goes up. And that is the whole secret right there. That's how it finds the weak links. The algorithm literally just does a test run for a bunch of tokens. It asks, if I remove this token, how much does the badness score go up? The tokens that cause the tiniest little increase in loss, those are the weak ones. If getting rid of a token barely makes things worse, it means it wasn't that important to begin with. It's just a spare piece of marble. So chip, it's gone. Okay, so we've gone through the whole process. The chipping, the carving, the refining. What are we left with? What does the finished sculpture actually look like, and why does any of this matter? All right, let's wrap this up with the key takeaways. What makes Unigram so cool? First, it's a subtractive method. Remember, it's a sculptor, not a builder. Second, it's all about probability. It's always looking for the most likely path. This has a neat side effect. It allows for multiple good ways to tokenize the same word, which gives a model a lot more flexibility. And finally, a huge one. Because it's part of SentencePiece, it works on raw text. It doesn't need spaces, which is a game changer for a ton of languages around the world. And that leaves us with one last thing to chew on. Think about it. We've just seen that one of the best ways to teach a machine about language isn't to give it a strict grammar book with a bunch of rigid rules. It's to let it figure out the most probable path on its own. So if our most sophisticated language models are being built on a foundation of probability, of what's most likely, instead of absolute certainty, what does that tell us about the nature of language itself? Kind of makes you wonder, doesn't it?